All right, so continuing with our t distribution values. So we notice that it's got degrees of freedom issues, namely that there's infinitely many t distributions, and which one you're looking at depends on your degrees of freedom, which in this case is your sample size minus 1. Then we notice that they are all centered, right here, centered around 0, right, like that. Every last one of them, and symmetric about that 0. Oops, I don't have an ability to insert a text box there. Let me try this. There you go. 0. Okay. So they're centered around 0. 0 is the line of symmetry. Right there. Okay. All right. Then the area under the curve. Well, the area under the entire curve has to be equal to 1, right? Because it's still a probability distribution. And probability distributions, as we learned from chapter 5, have to have an area equal to 1. All right. Let's see. What about the area to the right of 0 or the area to the left of 0? Well, if the whole thing is 1 and it's symmetric, then doesn't that automatically mean that half of it's on one side and half of it's on the other? So what's the area to the left and the right of 0? It's 0.5. All right. As t increases without bound, the graph approaches but never equals 0. That's the whole horizontal asymptote thing. The fact that they get closer and closer and closer to the edges, but they never get there. The area in the tails is, the area in the tails of the t-distribution is a little larger, a little bit more than, let's put it this way, more than the area in the tails of the standard normal distribution. Okay, and you could see it, let me remind you, right here. That's the standard normal distribution up here. This is the t-distribution down here. Notice the area in the tails is more. And I have for us drawn here, just so you can see, oopsie, there it is. I have some curves drawn, and I wanted us to look at them. So I have a blue curve, an orange kind of curve, and a green curve. And the question is which one's which? So the normal curve is this one. The gold standard, or in this case, the green standard. It's the best curve, it's the bomb. It's the one we wish we could get to use all the time. But unfortunately, when you're working with the mean, you don't know sigma, so you can't get to use it. So that leads us to the blue one and the orange one, and which one's which. One of them has degrees of freedom of 15, and one of them has degrees of freedom of 6. Okay. Well, keep in mind that the closer we are to, or let me put it this way, the larger your sample size, the better, right? So if that's the case, then if you look at these curves, which one's closer to the green one, which is the normal one? This orange one, right? So that must have the larger sample size, which means the DF is 15. So if the DF is 15, that means that the sample size was 16 for that one. And this one over here, much shorter, much fatter tails. Look at those tails over here. Compare that blue tail there to that green tail on the normal curve. Right? It's got a much fatter tail, which means that's the DF equals 6. Okay? The smaller your degrees of freedom, the shorter the height, the fatter the tails. The bigger your degrees of freedom, the closer the curve gets to the normal curve. All right, done with that. Now, determining the critical t value in each of these cases. So, critical t values, you don't need to find them with the t table. I take that back. You can find them with Excel, because Excel finds them for you. All right, and I'll show you how. And we're not going to use the table, although you could, I suppose, but there's just no point. So let's go find a t.02 with 20 degrees of freedom. Well, let me wait for this to pop up. All right, now I have to be honest, this is something that's gotten a lot better in the latest edition. You use t.inv, you say 0.02, comma 20, enter, and there you go. The only issue is we want the one on the other side, but that's okay because you can just say 98 and you'll have it, right? All right, so that's that. And I'll be back for more on that on the next one.